Yeah, so in this problem, we're going to be looking over a binary tree, right? So we're going to be doing a lead code problem number 863, which is all nodes distance k in a binary tree. So we are given the root of a binary tree, the value of a target node target, and an integer k. So our answer would be an array of the values of all nodes that have a distance k from the target node. We can return the answer in any order, right? So basically, let us say we have this example. We are given the binary tree. Let us form it on our own. So we have been given 3, then 5, then 1, then 6, then 2, then 0. I'm going according to the array and forming my tree. Then 8, and then we have null. So once we have null, that means it has no values on the left. So left child is null and the right child is also null. And for 2, I have 7 as the left child and 4 as the right child. And here also we have null because no other values have been stated. So this is also null and this is also null, right? So this is our binary tree, and we have been given the target as 5. So this is the node that is our target node, and the value of k is equal to 2. So what our aim is to calculate all those nodes that are at a distance of k is equal to 2. So that would be basically node 1 because it is at a distance of 2, along with node equal to 7 and node equal to 4. So these are at a distance of 2 from the node 5. So that is why 7, 4, and 1 would be returned. Here also you can see 7, 4, and 1 because they are present at a distance of equal to 2 from the node target, that is 5. Right, so that is about this example. Then we have another example, that is root is equal to 1 and the target itself is equal to 1 and k is equal to 3. So there are no other nodes in this tree. So basically the answer would be an empty list because no nodes would be at a distance of 3 from it, since there are no there's no left child or right child for this node. So basically we need to model this problem into a graph problem, and let us go over the solution, how we're going to be thinking about it. So we'll basically be performing BFS, right, to basically get a level wise traversal for the whole graph. So since we are given a binary tree, a target node, and an integer k, and we have to find exactly k distance away all the nodes that are present from target node. So each node typically has pointers only to its children, that is left and right, but not to its parent, right? And our aim is to also go over to the node that is the parent, right? Since we need to traverse from 5 to 3 to 1, right? So this is a binary tree, but in order to move up or down in the binary tree itself, there's no function for that. There's no pointer for the going up in the binary tree. So we can't reach the parent from a particular node. That is why we need to track it ourselves going to the parent. So we must convert the binary tree into an undirected graph. That is where you start to build your intuition from, that since we are traversing up also in the tree, we need to store it into an undirected graph so that we can traverse in all the particular edges where each node is connected to its children and its parent. Then we can perform a BFS from the target node until we reach the kth level. All nodes at the level will be our answer, right? So our approach is something like this. So what we do is we search for the target node. A helper function search recursively locates the node with the target value. So in the whole binary tree, our main aim is to basically first go over the binary tree and search for the target node that has been given to us. Then create the parent links for each node. So we use a BFS traversal to map each node to its parent in a parent's hash map. That is unordered map tree node star, tree node star, which would be containing the node, containing the particular node and its corresponding parent from the tree, right? So this is useful in building the graph. So now we apply third point is BFS from target. So that is step 3, where we initialize a queue starting from the target node. So starting from the target node, we can traverse in 3 directions. That is up, that is towards the parent, or towards the left child, or towards the right child, right? So these are the 3 directions that we can traverse. And we also track visited nodes using unordered map, node, tree node star, and bool of this type. So that would be storing the node and the bool value, that is whether it has been visited or not, so true or false. So this is the format of the visited nodes to keep a check on whether the node has been visited or not. And finally we stop BFS when our level becomes equal to k, right? So this is our stopping condition, and we collect all the node values that are at this particular level, right? So that is why we are performing level order traversal. And the time complexity, let us discuss. That is O of n. N is the number of nodes in the tree, because O of n we need to use to build the parent map, that is the unordered map, and also for the BFS traversal up to k levels, and also the space complexity O of n for the parent map, visited map, and BFS queue. Now moving on. So this is basically our solution. So let me go over each and every single point. So basically, firstly, what we do is our search function is used to search the node with the target value in the binary tree. So recursive BFS to find and return the target. This is our search function, and we have the mark parents function to basically map each child to its parent for all nodes in the tree. And our main function is distance k function. So this is quite a long function. You might think it is complicated, but I'll break each and every step down, and show you how you can solve this very easily. So basically what we have to do is initially we make a map of type tree node star comma tree node star, which is named as parents, which will store the particular node and the parent. So we need to keep the parent also, because we can traverse in 3 directions, that is the left child, right child, for which we already have pointers, but for the parent we don't have any pointer, right? So that is why we need to have a store of the parent. So for that we have unordered map of parents, and also visited unordered map that would basically store the node and whether it has been visited or not, that is true or false, right? That is why we have bool here. Now we call the function mark parents, that would basically take in the root, that is the particular node that we are starting from, and it would be taking parents. Parents is basically this map, so that the parents map would be updated in the mark parents function. And let us go over to the mark parents function. What it does is it maps each child to the parent for all nodes in the tree. So you can imagine it as a normal BFS function that is being used in order to map all the nodes to their corresponding parent. So basically we have the parent and the node, right? So let me show you exactly how it's working. We maintain a queue of node star type, t node star type queue, push the root in it. So the root would be pushed to the queue. So this is a queue, let us say we are maintaining a queue. We push the root in it, the root value has been pushed, and while the queue is not empty, we we extract the queue dot front and assign it as node, sorry. So queue dot front is node and we extract it from the queue. So this value is node, basically it takes the value of root. Now we check if the node's left child exists, then we push the node's left into the queue, and if the right child also exists, we push that into the queue as well. And also while we are pushing into the queue, we will also simultaneously be marking the parents of the node's left as node. So parents of node left, so parents of this particular node's left child, basically let us say this is value 1, right? So for this parents of node left would be 1. So this node would be assigned to the node, right? And this is the node. So we have what we have done is basically store the parent of this particular node. Similarly, if this is the right child and if this has a value of 2, then it would store the value of 2 and the node that is 0 in this format. So the parent is here and the node being stored is here, right? So this is the explanation that the parents basically left child and right child have mapped to the parent, right? Mapping left child and right child to parent. So this is what we have done in this function. And basically the map, when we come out of this function, mark parents would basically return us the parents that has been updated with the node and the parent. So that is updated here. So the parents is going to now have all the node comma parents mapping, right? And now we maintain a queue to start the next BFS. So we basically taking queue of node star type, and the target node is basically achieved from the search function, which basically target has been assigned to us. So we send the target's value and the root to search. So this is basically done using DFS function, where we search and get the target value in the graph that we're searching for, right? So if root is null, return null. If root's value is equal to target, that is if the node that we are present at, that itself is the target value, so we return that. Otherwise what we do is we go left and we call the roots left recursively. So we call the search function again and we call roots left. So we look over this subtree to check for the function, to check for the target. So if left is not null, that is if left subtree exists, if left child exists, then we return left, and if the right subtree right child exists, then we return that. So basically when it recursively checks, finally when it comes, it would check here if root's value is equal to target. So in either of these subtrees we find the target value and we basically return that target value here, return root. And in case we are not able to find it, we return null, right? So that can also be the case. In that case we return -1, right? So basically now target node is containing the value, or basically the node where we actually want to start our traversal from. So BFS traversal will start from target node. Here is the check: if target node is equal to null, then we return an empty vector if the target node is not found, because then the traversal won't happen, right? Now we mark the target node as visited, right, and push it into the queue, since we are starting BFS from target node and traversing from there, right? Now here is the main function, that is we mark current level as 0 and answer vector, in which we'll store our final answer, that is all the nodes that are at distance k from the node target, right? So standard BFS approach, we apply that while the queue is not empty, n is equal to q dot size, where n is the number of nodes at that particular level, at that current level, and we check if the current level has become equal to k, that is now we have reached the distance equal to k, that is we can now basically from the target node we have reached let us say this was the example that was given to us. The tree was something like this, right? So this was the target node, right? This was target. So from this node, and k is equal to 2. So if the level equal to 2, that is, while we have traversed from the BFS, I'll show you, this is the first level, right? These are the nodes that are present at level equal to 1 from target. This is level equal to 1, and this is basically level equal to 2. These are the nodes that are present at level equal to 2. That is, from the target, we are at distance 2 from these nodes, right? So if our level has become equal to the k value, that is equal to 2, then we can basically add the nodes at distance k to the result, because these are the answers itself, right? These are the answers. These are going to be appended to the final vector. So for I is equal to 0, I less than n, that is number of nodes at that level, we pop the node out from the queue and push the node's value, collect all those node values, and push it into the final answer that we need to return, right? And we break, because we don't need to go to the level 3 now, since at level 2 we have found our answer, right? Since we have gotten nodes at distance k from the target node, so we don't go deeper here. This is the check when we have reached the level k. In case we haven't reached, that is, we are still at level 1, right? So we start from that level, and for I is equal to 0, I less than n, so we traverse all the nodes at that particular level, get the node out from the queue and pop it out, and then we check if the node's left exists, that is, if the node's left child exists and has not yet been visited. So if this has not yet been visited, right, we push it into the queue and mark the visited of the node's left child as true. Similarly for the right child, that if the node's right exists and the left and the right child has not yet been visited, we push it into the queue and mark it as visited, right? The standard BFS that we do. And here also another condition would be applied, that since we have a graph, right, we are considering it into a graph, as a graph, so we have to go up as well, right? So for the parent as well, if the parents of node, if the node's parent exists, that is, if it is not the root of the tree, so its parent would obviously exist, and it has not yet been visited, right? If it has not yet been visited, then we push it into the queue and mark the visited of parents of the parent as true. And finally, when we are done with this, this is, let's say, level 1. When we are done with this, we increase the level to level 2 by incrementing it. So we move to the next level, that is level equal to 2, and finally basically it keeps on running iteratively and keeps on checking till the time the queue is not empty, and it keeps on checking if current level has become equal to k, right? And in case k is basically a distance which is, let us say, for this graph itself, if k was assigned to us as 5, so that would not have been possible. So the answer would basically be an empty list itself, because the maximum distance from the target node is equal to 3, right? So anywhere you check, this is equal to 2, this is also equal to 2, this is equal to 1, this is equal to 1, then this is also equal to 1, 2, and 3. So you can see the maximum distance from the target to any of the leaf nodes, any of the remaining nodes, is equal to maximum distance is 3. But if we have k is equal to 5, since we don't have any levels more than 3, we cannot reach any other nodes, right? So for that, the list would have been empty. So that's how you solve this problem. Also, once we basically get out of this loop, we return an answer that is all nodes at distance k. So let me just show you after running this whether it's getting accepted or not, right? And yeah, it has been accepted.